Hello, my name is Bonnie Baker, and welcome to the web seminar about Do I Filter Now, Later, or Never? We're going to talk today about analog filters and digital, and we're going to compare the two kinds of filters and whether or not when we use them or when we just don't use them. Then we'll plop into talking about analog filters specifically, and then we will end with the digital filters. Okay, this slide's talking about analog versus digital filters. You know, a question that I get from a lot of customers, they say, do I need an analog filter if I'm only looking at a DC signal? Come on, a DC signal, there can't be any noise. DC by definition means no noise. Is that correct? And I look, and I talk to them, I say, yeah, you do need a filter, analog filter preferably, because your electronics just doesn't know that you have the intentions of looking at just the DC portion of the signal. As a matter of fact, your electronics will send through any kind of frequency content through to the A to D converter, and despite your desires. And the second question I get out in the field from a lot of customers is, do I need an analog filter as opposed to a digital? And the answer to that question, again, I come back and say, well, yeah, you do need an analog filter, and simply because once the signal is converted by the A to D converter, the contamination, and I put quotes around there, the contamination of the noise is there, and it will be aliased back into your digital results. You can get rid of it. It takes time, and it takes memory to eliminate it. And maybe you can't get rid of it. A lot of times I've run into signals where you just can't eliminate it. And the second answer to that question, as an analog filter opposed to the digital, is the analog filter will eliminate effects of the overdriven signal to a certain extent, much, much more than the digital filter will do the same. And these effects of an overdriven signal actually happen well beyond the bandwidth of your signal and the thing that you are really interested in testing and looking at. So let's talk about this. When to pick an analog over a digital filter. You know, if you look at the diagram there on the bottom of the slide, it says analog input signal, and that goes into the analog low-pass filter, followed by the A to D conversion, and then into a digital filter. Now that's a position of these filters in your signal path. You can't put the digital filter on the analog side because by definition, you're dealing with analog signals, and you can't reverse the position of the analog low-pass filter into the digital side of things. Usually, digital filters are implemented using microprocessors or microcontrollers from Microchip. At any rate, going to the top of the slide, analog filters will reduce foldback noise, and I'll show you what foldback noise is. Another word for foldback signal is an aliased signal that the A to D converter will take signals and fold them back into and place them into the digital output code. Analog filters also will minimize, like I said before, the impact of the noise peaks in your signal. Now, digital filters are great. Don't get the wrong idea. I keep on harping about analog filters, but digital filters are great. What a digital filter can do is reduce the noise in the band, the signal band that you're looking at. Analog filters can't do that. They get rid of noise that is out of the band of your area of interest, but a digital filter can reduce noise actually in the band, frequency band that you're interested in. It also removes noise that is injected by your A to D converter. I'm sure you've heard of quantization noise and that kind of thing that an A to D converter will generate simply because you're breaking it into a discrete number of bits. And a digital filter can, I shouldn't say remove, I can reduce the noise that is injected during the conversion. And lastly, and the most attractive part of digital filters is they are really easy to program, much easier than analog filters. With the analog filter, you have to go in and you have to take out your hardware and resolder or maybe lay out the board and et cetera, which is time-consuming and expensive. But with a digital filter, with a few keystrokes and a little bit of knowledge, you can change the digital filter operation very quickly. So saying that, you say, well, I want to use a digital filter all the time. And let's start out talking about analog filters first out, and I'll show you the advantages and the features of the analog filter. Specifically, I'm going to talk about three types a Butterworth filter, a Chevy Chef, and a Bessel filter. There are other types like inverse, Chevy, or elliptic filters that I'm not going to touch on right now, but certainly you could use them. So let's go forward and take a look at that. Here's the frequency response of those analog filters, like the Butterworth, the Chevy Chef, and the Bessel. You'll notice with this filter that the lower frequency signals are just sent through. They just go into the filter and they end out at the output of the filter quite easily. But the higher frequency signals up in this area, that is cut off, or it's reduced and is gotten rid of. It's thrown away. On the x-axis, by the way, is frequency, and is a normalized frequency. And on the y-axis of this chart here, or this graph, is magnitude in dB of the signal coming through the filter. So that's pretty nice, that kind of characteristic. I'm showing here the fifth order Butterworth and the Chevy Chef and the Bessel. Those are the three types I wanted to talk about. But with these filters, there's a different filter response in the frequency domain. You can see with the Butterworth that you get a flat response as the passing frequencies. With the Chevy Chef, there's a little bit of ripple up there on top, and the Bessel is flat, but the Bessel attenuation over frequency is slower than any other of these filters right here. So, that being said, you have to also think about the time domain response of these three filters, and that's shown at the bottom of this slide in the bottom graphs. The time domain response on the x-axis is time, of course, and on the y-axis is amplitude. You'll note that in the time domain response, the Butterworth, as the first filter we'll look at, has a little bit of ringing that's occurring as with a step response going into the filter. And that ringing will appear at the output of the filter. The Chevy Chef has a fair degree of ringing, and something that you may or may not be able to live with in your circuit. It takes a long time to settle. And the Bessel comes up, goes to its final value, and gets there in somewhat of a quick manner and settles in, and that's the end of that. So those are the three filter types that I usually talk to customers about in terms of using analog filters. You choose one over the other for the advantages in the time domain versus the advantages in the frequency domain. Well, I mentioned at the very beginning of this session, I talked about Nyquist, and I talked about fold back and that kind of effect. And I want to go into a little more detail. Analog filters can take out this fold back or Nyquist harmonic distortion that gets into your signal as it goes to the A to D converter. If you can imagine on these two graphs, you look at them, on the left-hand side of the graph is before the signal goes into the A to D converter. And on the right-hand side is after the signal comes out of the A to D converter. Now you can say, well, the right-hand side, those signals are representative is in a digital, a sampled kind of representation. And on the left-hand side, the representation in the y-axis is analog signal. Along the x-axis in both of these graphs is frequency. So let's look at this a little bit carefully, more careful. On the left-hand side, again, I have the analog signal coming into appearing in the before the A to D converter. And in this hypothetical signal, I have three potential signals with content, frequency content, different frequency content. You'll notice that one of them is above, or at a lower frequency, should I say, than f of s over 2. Number 2 is below f of s over 2. And number 3 is way, way up in frequency. And so the question is, what would happen when this signal goes into an A to D converter and it's converted? The A to D converter will take signal, the frequency number 2 and number 3, and fold that back into your digital results. And that's shown right here in this graph. It'll fold it back, number 2 and 3, and you won't be able to tell the difference between signal 1, 2, and 3 in your digital output code. It folds it back. It contaminates the frequency content, but it does not contaminate the magnitudes. So therein lies the problem. The formula to describe this phenomena is shown here at the bottom of the slide. F alias is equal to the absolute value of the input signal minus N, which is up along the top of my graphs there, N times F of S, which is the sampling frequency. So you're going to have signals coming back into your digital code, and you won't be able to separate them out. There's only one way of getting rid of that problem, and that is putting an analog filter into your circuit. So let's step into the digital realm, because I'm kind of fond of that. It's easier to program, easier to change digital filters than it is analog filters. And we'll talk about the infinite impulse response filter, the moving average, and finally the finite impulse response, which is the FIR filter. The IIR filter is basically, it actually copies the analog filter frequency response that we saw earlier on. Down here I'm talking about the Bessel and the Butterworth and the Chevy Chef, and you can design any one of these 3 plus more types of filters in the digital domain. What's the issue with this filter? It will give you the same frequency response, but it will not remove those alias signals that already got into your digital code before through the A to D conversion process. So it's an interesting filter, interesting strategy, and could be useful. Another kind of filter is the averaging filter. This is the most common digital filter that I hear about from customers. You just take several codes. Say in this example, you're taking 4 codes, and you're adding the 4 codes together, and then you're averaging them. Well, depending on the codes and the average of that, instead of, in this example, getting a 1 or a 0 on the output of your digital filter, you can get a 1 or a 0 or a 0.25 or a 0.5 or a 0.75. So you've increased the accuracy and number of bits that you have, and you can zero in, because of averaging, on something that is halfway between 1 or 2 codes, or even more so. As a matter of fact, you can use this and extrapolate this even further. If you oversample, and that's what we're doing, we're taking several codes on converting and taking in several codes. If I oversample and I add those codes together and divide by and take an average, for every 4 codes I take in, 4 codes I oversample, I'll get a 6 dB improvement in the signal-noise ratio, or I'll get 1 bit improvement in my conversion just with my digital filter. If you take that and extrapolate that out, that I can add 2 bits. If I start with a 1-bit AD converter, I can get 2 bits out of that by having 4 times oversampled and divide by 4. I can get 3 bits by 4 squared, which is 16 times oversampling, or I can get 4 bits by oversampling 64 times and dividing by 64, etc., etc., etc. I can get 24 bits, theoretically, by oversampling 4 to the 23rd times, and that's a big number. Do you have time to do that? Well, maybe you don't, because you have to take in the samples and you have to divide by. Lots of time and lots of memory space in your controller. So it does reach a limit of no return. Another kind of filter is the FIR filter, FIR, finite impulse response filter. And this filter uses the same kind of technique we just described. But throughout this filter, you have a unit delay, as we had before, and then you weigh each of the codes coming in. And by doing weighing, you can get a little bit better response, a little bit of better filtering coming out of this. The consequence of doing a rolling average or even this FIR filter is there is latency that's built in. For instance, here's the input signal right here, and here's the output signal, and the output signal has been delayed because of the mathematics that have to be performed by the digital engine. Here's a frequency response of a FIR filter. This is 3 FIR filters just cascaded together. The frequency response at DC is really quite good, and it attenuates the signal up in frequency really well. It goes down to 60 dB down. That's a third order filter. But you will see the comb effect with the FIR filter coming through again and again, which is all well and good if you, on the front end, put in a little RC filter going into the A to D converter that has a digital filter in it. Then you can get rid of the higher frequency stuff. The time response of this filter is shown right here, which is somewhat awkward, but it takes a while to get to the full step. In this particular filter, I put in, again, a step response and took digital code out of this device, and this is the kind of response I got out of the filter. Okay, so what's the best design approach when you do this kind of thing? Well, first of all, if you're working with sensors and that kind of thing, of course you will want to gain the signal, and you may want to use a multiplexer. But at any rate, just before you go into the A to D converter, you use a low-pass filter. Now, I'm indicating the A to D converter with this microcontroller block because Microchip has a lot of A to D converters inside their microcontroller that you can use. So the low-pass filter goes before you digitize the signal with your A to D converter. So there's your low-pass filter. And the digital filter goes in, of course, a microcontroller that works on the piecewise linearization that you might have done with the signal, and then it goes out to an actuator that excites a valve or something of that nature. So, returning to home base again, analog filters are always located before the controller or before the A to D converter, better said. They reduce the foldback signals, the aliasing signals that you cannot get rid of after you perform an A to D converter. It's there and it's embedded in your signal at that point. And it minimizes the impacts of noise peaks in the analog domain. Now, a digital filter, of course, is located in the controller, and it can reduce what I call, oops, that was a misspelling, in-band noise. It can reduce in-band noise that we discussed, and it also removes noise that's injected during the conversion, which we talked about doing that as well, which is in-band noise. And finally, the nicest feature of a digital filter, it's easy to program and easy to change. I have put in this presentation some references. It's a limited list of references, but you can go back and take a look at it. The app notes ADN03 is selecting an op-amp for your filter, and then you'll get some help in ADN699 in actually designing an analog filter. And there's some help here using a digital potentiometer in designing your analog filter, which you can use to program. We also have app notes that help you implement FIR and IIR filters and signal processing using the PIC16C74. Those are useful application notes. In terms of books, I have Analog and Digital Filter Design, which is a great book because it talks about both of the issues. And the digital signal processing book listed here is quite good too. There is an article that's out that went into EDN. Do I filter before or after? And it kind of repeats what we just talked about. And finally, if you need help designing analog filters, the Filter Lab program that you can get for free from Microchip on our website is a very useful tool to get you from A to B. That concludes this presentation and this seminar. I hope you enjoyed it. And if you have any questions, please email back to the factory and I'll be happy to answer them. Thank you very much. Again, my name is Bonnie Baker, and have a nice day.